Today, we're unpacking an absolutely fascinating breakthrough out of MIT. They're promising to solve one of the most pressing data and energy bottlenecks in modern computing, and they're doing it all by harnessing the incredible power of light. So here's the big question. How exactly do we feed AI's massive, insatiable hunger for data without literally melting our power grid? I mean, it sounds like a tagline for a sci-fi movie, right? But it's actually the exact real-world crisis brewing inside high-performance data centers all over the globe right now. AI models are just exploding in size. Cloud services are expanding nonstop, and our conventional hardware is quite literally struggling to keep up with this insane demand for speed and power. Okay, here's our quick roadmap for today. We'll hit 1. The AI data bottleneck, 2. The photonic solution, 3. MIT's optical solder bumps, 4. Reaching petabit speeds, and finally, 5. Building a greener future. Let's jump right in. Section 1. The AI data bottleneck. Let's start by looking at the actual physical limits we're hitting right now with our conventional electronics. We've got this exponentially growing demand for speed when it comes to AI and cloud computing, right? But as data rates climb higher and higher, those traditional electrical signals run into massive physical resistance in the wiring. And that resistance, well, it leads to severe power loss and generates an unbelievable amount of heat. Essentially, trying to shove more data through traditional electrical interconnects just drains more and more energy, which makes data centers gobble up an ever-growing chunk of global electricity. We are, quite literally, hitting a physical wall. Which brings us to Section 2, the photonic solution. To smash right through that data wall, the semiconductor industry is desperately looking at a totally different kind of technology. It's called co-packaged optics. Basically, this is the integration of electronic processors, the parts that use electricity to do the math, with photonic chips, which use light to transmit the information. Now, engineers have known for a while that this is one of the absolute best ways to drastically improve how fast data moves inside servers. Optical communication uses way less energy than forcing electrical signals through copper wire. But there's always a catch, right? Historically, marrying these two worlds, taking delicate photonic chips and slapping them directly onto conventional electronic processors, has been incredibly difficult technically and just prohibitively expensive. So the core philosophy behind MIT's new approach is actually super simple. Let electricity do exactly what it does best: heavy computation. Let it do the thinking. But when it comes to moving that data around, rely on light, or photonics. Light can transmit enormous amounts of information across vast distances with virtually zero physical resistance, making it absolutely perfect for high-speed talking. By separating the thinking from the talking, you can drastically cut down the overall energy demands of our future computing networks. It's brilliant. Moving right along to Section 3, MIT's optical solder bumps. Zooming all the way down to the micro level, we find the concrete hardware solution developed by MIT's Photonic research program to actually make this integration possible. They've created the optical equivalent of solder bumps. You know how in traditional electronics you have these little metallic solder bumps linking chips together to conduct electricity? Well, MIT researchers have somehow managed to create optical versions of those. Instead of carrying electrical current, these tiny optical components seamlessly transfer light between the photonic devices. This completely simplifies the packaging process and makes assembling these crazy complex electronic photonic hybrid chips a much more realistic manufacturing goal. So let's walk through how this integration actually works in practice. Step 1. The system computes the data using those conventional electronic processors. Step 2. The signals are transferred through the newly engineered optical solder bumps we were just talking about. And Step 3. The data is communicated at the speed of light via photonic chips. But here is the real game changer, the thing you really need to take away from this. This entire process is designed to be manufactured using today's existing semiconductor production equipment. The industry doesn't have to go out and build entirely new multi-billion-dollar factories from scratch to make these. They can adopt this for large-scale production so much faster. That is huge. And that brings us to Section 4, reaching petabit speeds. Now, to make these mind-bending data speeds a reality, MIT didn't just try to force a one-size-fits-all solution. Instead, they engineered specific optical couplers optimized for very specific design needs. For example, the GRIN, or graded index coupler, gives you broader wavelength compatibility, so it's perfect for handling a really wide range of optical signals. On the flip side, the evanescent coupler is way easier to fabricate and packs much more densely. That's exactly what you want when you need a massive number of connections in a super tiny area. They're also pulling in a third coupling technology developed previously by Professor Ju Junhoo's team. So future systems will likely just mix and match all of these technologies to get the perfect balance of manufacturing ease and integration density. And all of that incredible microengineering leads directly to a frankly massive leap, 1 petabit per second. To put that into perspective, today's standard data transmission is measured in hundreds of terabits per second. But the ultimate goal of Futuristic Director Anu Agrawal is to completely shatter that standard. Pushing data transmission beyond 1 petabit per second isn't just a nice little upgrade. It is a completely new paradigm for computing power. We're talking about a whole new ballgame here. Finally, let's look at Section 5, Building a Greener Future. Looking at the big picture, the macro-level impact here, the Future IAC program actually goes way beyond just building faster hardware. They are taking very active steps to track and mitigate the tech industry's environmental footprint. For instance, they've launched EarthStar, which is this powerful modeling platform helping companies evaluate the true environmental impact of manufacturing semiconductors. It helps them pinpoint exact hotspots for energy use, material consumption, and carbon emissions. And in parallel with that, they are providing massive workforce training through online courses and boot camps, actively educating the next generation of engineers on resource efficiency. It is such a wonderfully holistic approach to the problem. And it all really boils down to this prevailing consensus right now. Photonic integration is widely viewed across the semiconductor industry as one of the most promising approaches to improving bandwidth without a proportional increase in power consumption. This basically anchors everything we've explored today. If we want faster AI and more robust cloud computing, we absolutely cannot just keep pumping electricity into traditional copper wires. The heat and power loss will literally burn us out. Photonic integration is, for sure, the definitive answer to this energy crisis. Which leaves us with this pretty provocative thought to chew on. As light replaces electricity to power the communication of AI, what new limits will we break next? Now, while commercial deployment of these exact chips might still be a little ways down the road, MIT has just successfully knocked down one of the industry's most persistent technical bottlenecks. We are standing right on the edge of a limitless, highly efficient petabit speed future.